So let's talk a bit about chapter 12. So this should be relatively straightforward.
Mr. Crew, what did you think about those themes for Iron Hills? Like, real talk.
Awesome.
Really?
I like ours.
I wasn't really feeling the vibe.
I for sure thought our grade was going to be student pick well.
That was unfortunate. The freshman got that.
Well, they had other options.
Well, that's just wet jungle.
I feel like West is.
Are we doing more geometry?
No.
Oh my god. No. I hate geometry. I kind of like.
How'd the test go?
I haven't graded them yet because
Why?
I forgot them on
Or something?
I forgot them on Friday, and then I forgot about them this morning until after lunch. And I was like, oh yeah.
Well, think about it this way: if you don't grade them, you just get us all A's.
Yeah, just
Spend
do
more time
that.
to grade
It'll
them.
be like
No,
no,
but
but
actually
have to grade by.
I am gonna grade them, but they'll probably be okay. Who knows?
We're almost on break. Just let it
I made one error and
So, chapter 12, I guess the way I would look at this is if you didn't feel very good about how the last chapter went, this chapter should be pretty easy. Okay?
Why would it work like that?
Just how it goes sometimes.
Wouldn't it be the other way around? If you did good in the last chapter?
Well, this has no geometry in it, so
Really?
there's no shapes.
Is there any numbers in this book?
There are some numbers, though.
Boo.
It's been cool without running
Harder with it.
Numbers are the favorite. Like, I guess numbers is better than letters.
I would rather run like.
So, chapter 12 is about polynomials and correlation, and specifically, I guess we'll get to it. I'm not going to worry about it right now. So we'll start just by defining what we mean by a polynomial function. So a polynomial function is a function that can be written in the form those are A's, yes.
I want more geometry. Is the n a subscript?
Yes. So polynomial function is of the form a sub n times x to the n minus 1 plus a sub n minus 1 times x to the n minus 1, and that just keeps on going until we get a sub 1 x to the first plus a sub 0. What's written is correct.
So it's n is a positive full number and each ai is a what?
Real number. Yep.
Okay, I was really.
Yep. So the
It's like Southern Cal, that's Cal.
I wrote the cow.
Southern Cal.
there we go. Okay. And the first coefficient there is non-zero. Okay. So these guys, the A's, are the coefficients. Right? So those parts are the coefficients. The X's are the, wait for it, variables. And these guys are the exponents. So just as a quick little example, let's say n is 3. Yep, in blue. So if n is 3, what this would say is a sub 3 is equal x to the third plus x to the sec, or a sub 2, x to the second, plus a sub 1, x to the first, plus a sub 0. Right? That's what the form would, or that's an example of a polynomial. Right? Is everybody okay there?
So, n equals 3, does it just, it just decreases by 1 in each position.
Exactly right. Yep. That's all that's going on. So what we did here, normally when we describe a formula like this, you remember for quadratics we called that ax squared plus bx plus c, where the coefficients we named with different letters a, b, and c. Here we're naming the coefficients with these a sub n's. The reason we're doing that is because a polynomial could have more than 26 terms. Now, we won't work with one like that, but it could, in which case we could run out of letters in the alphabet to use. But if we're naming them with a subscript with a number, we have as many like coefficient names as we need. Does that make sense? Because you have like a 10,000 term polynomial. Yuck. We won't deal with that in this kind of a class, but that's all that's going on here. Okay? So, two very special parts of this formula. We say that n is the degree of the polynomial. So in that previous example, we had a degree 3 polynomial. And that a sub n is the leading coefficient. So let's do a couple of examples. So we're going to start, I'm going to write down a function, and you're going to tell me yes or no if it's a polynomial. And if it is a polynomial, let's also write down then its degree and leading coefficient. If it's not a polynomial, we can't answer those questions per se. Everybody cool with that plan? So what about, oops, I guess that's not a function because it didn't have a f of x in front of it, right? Okay, sorry about that. Now, is this a polynomial function? Why do you say no? Well, let's look at the coefficient, or the exponents. Are those exponents positive whole numbers? Yes. Okay. Let's look at the coefficients. Are the coefficients real numbers? So is it a polynomial? Yes. Yeah. Oh, well, it surely does. It just would be 0x to the 5th, 0x to the 4th, 0x to the third, etc. They're there. We just don't have to write them down because their coefficients are 0. Is everybody's okay with that idea? We can see now you're convinced, okay, surely this is a polynomial, right? Okay, what's the degree here? 6, that's correct. How'd you get that so quick? It's not just the first one though, it should also be the largest, yes. Doesn't have to necessarily be written in descending order, although that is the standard convention that we would write it. And then what's our leading coefficient? 4. Everybody's good with that? So whatever the coefficient on that highest degree term.
So it's not necessarily the first one, but the one with the highest degree.
Yes. Do you guys know what I mean when I say term? So each one of these little like addition or subtraction pieces is a term. So this has 4 terms. We don't count the 0 things as terms, just FYI. So like the 0x to the 5th, 0x to the 4th, we don't count those. We count the number of terms. Okay with that? Let's do another. So what about g of x equals the square root of 3 times x minus 6? Is this a polynomial? Why do you say no? Okay, well it's, what are the exponents positive whole numbers? Right, that's a 1, that is. Are the coefficients real numbers? So is it a polynomial? Yes. So what's the degree here? 1. And what's the leading coefficient? Square root 3. B, C, D, E, F, G, H is the next letter. Is this a polynomial? You say yes. Why do you say yes? So the coefficients are real numbers, sure. And the exponents are positive whole numbers. But what else is happening to the variable here? There's a square root around the variable here. Notice in the previous example, the square root was not around the variable, it was just around the number. This answer is no, and it's because the square root is also over the variable. That's the issue. If you go back and look at the original definition here, we don't have square roots around any of the variables. That's not an option for us. So this one is no. Everybody okay there? Okay. Not from this class, but somebody might be in there. You wouldn't know until you got there though. I don't have a camera into the bathroom. That would be weird.
This is not a function.
Good. Why is it not a function?
-1.
Very good. We have an exponent that's not a positive whole number. Okay. What do you think? So far, pretty easy, right? Just using some definitions, right? Okay. So let's now look at some names of some common polynomials. So the most basic trivial polynomial is called the zero function. The equation for the zero function is y, or f of x equals 0, or y equals 0. And the degree for this is defined as undefined. That's mostly from convention. There's not a good intuitive reason why that degree would be undefined. The next one is the constant function, where we say f of x is just equal to some constant a. And just to differentiate that from the possibility of the zero function, we say that this a is non-zero. So it could be like a equals 1, or a equals 7, or I'm sorry, f of x equals 1, or f of x equals negative 7, or f of x equals the square root of 17, or whatever. It's just some number. In this case, we say the degree is 0. The next one is the linear function. Where we write f of x equals ax plus b, or you probably think of it as mx plus b, right? This is a degree 1. And we have the quadratic function. F of x equals ax squared plus bx plus c. Again, where a is not 1, I'm sorry, a is not 0. And this is a degree 2. So this is just a little vocab drop, right? These are hopefully, these 4 names sound relatively familiar, especially like the last 3. And the form of them should look relatively familiar, right? Maybe with a little bit of letter replacement. But these are basically things that we've spent whole chapters talking about in previous classes, right? Your Algebra 1 class, probably at least 50% of that class was spent dealing with linear functions. Your Algebra 2 class, a large portion of that was probably spent dealing with quadratic functions. These are 2 things in particular we've spent a lot of time kind of learning about throughout your mathematics careers. What we're going to move on and start talking about now is correlation. Let's say is a numerical description of how, let's call this actually linearity of 2 data sets. So the symbol that we use for correlation is the lowercase letter r. It's the symbol we commonly use to represent correlation. Now this scale for correlation goes between -1 and +1. When r is close to 0, we say there's weak correlation. And when r is close to 1 or -1, we say that there's strong correlation. So the picture I've drawn here below is the same thing that I'm describing there above in words. I'm just describing this relationship now visually. So like that solid black line's like a number line. Okay. So let's kind of just think very generally about some examples of this. So correlation is describing the linearity between two data sets. So for example, maybe your two data sets are age and height. Is there a relationship between the age and height of a person? What would you describe that relationship as, just in words? So as what goes up? So as you get older, your height goes up, gets bigger, right? Up until a point anyways, right? And then what's going to happen? Kind of. Yeah, so if we were to graph this, it might look like something like that, right? Where actually that's probably should be, and then really long, and then maybe a little tail off at the end. So maybe this would look like what our relationship is. Now, does this look exceptionally like a line? I mean, it does for a little while, but then we have this big flat part, right? Maybe if we look at the relationship between age and height of an individual, like up until 20 or so, that's probably a little bit better we probably see a little bit more linear of a relationship, but really maybe up until even 15 or 16, where we do most of our growing is done by that point. You know, unless you're a late blooming boy or something that grows, you know, like a foot in your senior year of high school. Like, you know, I don't know, like didn't Kevin Durant grow like a foot like almost in the last year of his high school career or something? I think I remember hearing that as a story. Yeah.
Yeah, I think you're right.
That's why,
Davis
like,
for 7.
yeah, that's why you were like, they have guard skills and they're 7 feet tall. Is because they spent most of their time playing the guard position, then all of a sudden they end up 7 feet. Way late. Okay, so that might be what that looks like. Let's look at another pair of variables or pair of data sets. So maybe our two data sets is the temperature it is outside and the number of times a small child washes their hands during the day or whatever. Well,
In the summer, they're outside, they also come back in.
yeah, I think that's a valid argument. Caleb says when it's nice outside, you're going to spend generally more time outside playing and would likely wash your hands more often coming back inside. What else would you frequently eat when it's warm out? Ice cream or like a popsicle or something? Are these typically easy things to eat for a small child? Yeah, these are typically messy things also, which probably would require a fair bit of hand washing. So would we expect to see some kind of increase there? Possibly, right? Now, is there a causal relationship here? Is the temperature causing the children need to wash their hands? No, it's really due to some, yeah, it's indirect, right? It's the circumstances surrounding a warm temperature. So these may not be causal. Yeah, so there is a big difference between like causation and correlation. So my example always is, this is a magic tape dispenser. It deters tigers. I've had this tape dispenser on my desk for like 10 years. Not one single tiger has shown up in my classroom. All because of this tape dispenser. I will sell this tape dispenser to you for $1,000, and it is an excellent tiger repellent. Do you buy this argument at all?
Well, you're technically not wrong.
Only a little.
There's a strong correlation here, but do we really think that the tape dispenser is what's deterring tigers?
This is a rule.
If you throw it hard enough. I think it's the area.
Yeah, it clearly has to do with there's really no tigers in North America to speak of outside of zoos. So,
Detroit Tigers.
okay, fair enough.
Yeah, but they
So that's an example of something that's correlated but has no causal relationship, right? As opposed to, say, height and weight of an individual. As a person gets taller, they're typically going to get heavier simply because they're carrying more bone weight, right? Two people with similar physiques one person's 6 feet tall, one person's 5 feet tall, the 6 foot person is just going to weigh more because there's more of them. There's more bones, there's more skin, there's more. Yeah, there's more of them. Yeah. Everybody okay with that idea? Okay.
I am more human than you because I'm taller. There's more humans.
Okay. So we just kind of talked about that. I'm not going to write anything down there. So let's say that this is my two variables. I'm just going to call them generically x and y. You know. And let's say that these are the, if I graph the points in my data set, this is what they look like. Does this look like a line?
A lot of points.
Pretty good, right? Looks pretty linear. If I'm just looking visually, this might be strong correlation, or would likely be strong correlation. Yeah, you would have. Absolutely. This is very statistical. Versus something like this, what would we consider this picture? Does this look much like a line? Yeah, that's not much of a line, right? That's weak correlation. Is everybody okay there? So the way I like to kind of think about this is, if I were to draw like a band containing all these datas, the thinner that band gets, the better the correlation really is. So like if I tried to draw the same band over here, that's pretty thick, right? So the thinner that band gets, the better the correlation is. Is that okay with you guys? It's kind of what I'm visually looking for when I'm looking at a data set. Okay. So we have these two data sets, and we turn them into a graph, and we'd like to be able to use this data set to make some kind of prediction, right? One way we can do this is that we can create a line that kind of describes this data. So something like this, we call this a line of best fit. And it's basically a line that's as close as possible to all the data points in our data set. It doesn't necessarily go through any of the points in our data set, but it should be as close as possible to as many of them as possible in our data set. So what we can use that line for is then to make predictions. Say I'm interested in what the y value would be at this specific x. I can use my best fit line to predict what that specific y value would be. Is everybody okay with that idea? So when we do that in between our data points, like we have here, this is called interpolation. If I say had done it out here, that's outside of my range of data points, we call this extrapolation. Which one of these two predictions do you suppose would be more accurate? Interpolation is correct. Let me give you an example of why. Suppose we collected a data set on age and height. And our data set we collected from people that were, ages 7 to 12, as we looked at, the amount of growth that happens just during that time frame. Okay with that? slope going to be steep? Is that going to be like the steepest time for most people growing? Probably, right? That's probably where a good half of our growth happens during those ages. What if we use that rate then to predict how tall someone would be at 40? You would expect, it was going to be unrealistically tall, right? That's the problem that that can happen when doing extrapolation, is perhaps you have something where the linear relationship only exists for a certain amount of time or certain values of x, and then the linear relationship kind of fades away. So that's the risk you run with extrapolation, is maybe the linear relationship is really dependent over just a certain set of x's or certain range of x's. And you know for interpolation that the linear relationship still exists there because you've sampled x's in that range. If you're going outside of that range of x's, though, it gets a little dicey. Everybody okay with that idea? Okay. So correlation facts here. Yeah. Sure. Okay. So that correlation coefficient is always between -1 and +1. If that R value is negative, we say that that is negative correlation, and that would correspond to a best fit line with negative slope. So if R is positive, that would be positive correlation, and this would correspond to a best fit line with a positive slope. And when the absolute value of R is close to 1, or you can think about just when R is close to positive or -1, we say that there is strong correlation. We've kind of already mentioned that. And similarly, when the absolute value of R is close to 0, there is weak or no correlation. We don't even have to scroll anywhere. I didn't even scroll. It's amazing you're so fast. So as just an aside, while you guys are kind of writing this along, what would we say about a data set whose correlation is exactly 1? What would we expect the shape to look like? So it would be a line with a positive slope. The data points are going to form actual points on an actual line where every single one of those data points lies on that line. So we have data that's perfectly linear. Would you suppose that to happen very often in a real world setting? No. Okay. Similarly, if the R was exactly -1, you'd have data that was lying on exactly on a line with negative slope. Probably wouldn't expect this to happen in the real world unless you're measuring something that was like man-made, then possible. But even just the act of measuring, you're usually going to get some variance in there to kind of throw that off. What about an R value of 0? of exactly 0. What is that going to look like? So it's going to look random. The data points are just going to be kind of all over the place. Now, could you actually make a data set with 0 correlation? You can't. It's really more of a theoretical value. So you can get very, very close to 0 by using like a random number generator to generate your data. But it's not an actual outcome. Even in the real world, if you try to measure the relationship between two things that are wholly unrelated, and you go and you look for a linear relationship there, you're going to find your correlation is still not 0. It might be really bad, but it won't be 0. Is everybody okay there? So let's say we have a data set that looks like this. And I ask you to estimate the value for R here. Like, give me a numerical estimate. In words, what would you say? So you it's going down is not a description for correlation, although that does accurately describe what the data set is doing. So when we describe a correlation in words, you'd want to use like strong, moderate, weak, and then positive or negative correlation. Okay. Do you think, is moderate the best descriptor here?
No.
This is probably strong. I would probably say strong. In general, numerically speaking, so like strong, I would say maybe from 0.7 to 1. Moderate maybe like 0.6 to 0.7, and then weak is below 0.6. It's probably what I would say there. So in this picture, really if you gave me any answer that was like between negative 0.7 to say negative 0.9 for R, any number in there would be okay with me. I would give that full credit and say good job with no exceptions there. I wouldn't want negative 0.1 exactly because it's clear that these are not forming exactly a line, right? This data set isn't exactly linear, but it's pretty good. So if you had said 0.7 or negative 0.7, negative 0.75, negative 0.8, negative 0.85, negative 0.9, like anything kind of in that range would be pretty good. To get any better or past 0.9, I'd want to see things closer than this still. But this is probably anywhere in there would be reasonable. Okay. So let's say that we have an actual data set and we want to generate a scatter plot and a best fit line out of this. Okay. This is something we're going to use our calculator to do. So let's say you're running a store and this is the price you're charging for like a canned good. And then this is how many cans are sold when it's marked at that price. So I'm going to show you how to do this both on your calculator and then also using Excel. So if you'd like to follow along with your calculator, I invite you to do so. If you just want to sit and watch, that's fine too. Obviously, we're making a video. If you don't need to go back and look at how to do this at any point, you can look at the video. Okay. So I'll start just by turning my calculator on. And if I'm going to enter data into my calculator, I'm going to be using the stat button, which is located almost next to the left-hand arrow. And I'm going to use from the edit tab, I'm going to select the edit command by pressing enter. And now you should have a screen that looks like this. Do any of you have data already entered into your lists here? Okay, so if you do have data in your list, this is how we'll get rid of it. I'm going to move my cursor so that it's on the name of the list. So now my cursor is up here onto L1. I'm going to press the clear button and then the down arrow, and that'll wipe the entire list clean. Don't press the delete button. It does not do the same thing as clear. Those of you that had data there, has it now been removed? Okay, so into L1, I'm going to type my prices. Notice that I am not bothering when the decimal ends with a 0. And then into my L2, I'm going to type my quantities. So again, after I type in the number, I'm just pressing enter to move to the next line. And I use the left and right arrows to move in between the lists. Everybody okay to hear? We have our data sets typed in. Good. So the next thing I'm going to do now is I'm going to exit out to the main screen by pressing second and the mode button. And now I'm going to set up a scatter plot to graph this data set. To do that, I'm going to press second and the y equals. This opens the stat plot editor. I'm going to select plot 1. It doesn't really matter which one you choose. I'm going to start by turning this on. The first option here listed is the type. We want just dots or points, so that's the first option to build a scatter plot. I want my x value to be price and my y value to be the number of cans sold. So I type my prices into L1 and my cans into L2, so that is appropriate. And then I particularly prefer the squares as they're easy to see the points plotted. So I'm going to leave that option highlighted there as well. Next thing I'm going to do is go to my window, and I'm going to set a window here. So remember, the x coordinate is based on the price. What would be a good lower bound for my price? How about $1? You guys agree with that? Because it's a little bit less than the lowest price on my list. What would be a good upper bound? How about $3? Yeah, because that's a little bit more than my highest point on my list. And then how much would you think that this should go up by, like the tick marks on my axis? How about a quarter? Yeah, 0.25 sounds good. Let's do the same thing now with my y-axis. So what would be a good y minimum to pick here? 75 sounds reasonable. Okay. And a good upper bound? 250, 210, doesn't really matter. I heard 250 first, I'll go with that. It doesn't really matter though. Either of those would be appropriate. And going up by 25, 50, whatever, doesn't really matter. Those are appropriate guesses though. Everybody good with this? Okay, I want to do one quick thing before I hit graph, and that's going and making sure that if I had anything in the y equals menu, I get rid of that. So I just pressed y equals real quick to see if there's any graphs are going on in there to clear those out because I don't want them in my way. Notice though that when I go into the y equals menu, this little plot 1 is highlighted. This is another way to turn the stat plots on and off, is you can just go move your cursor up here and press enter to turn them on and off. Let's hit graph now. Woo, thank you. So there's my data set. There's the graph of this. What would you estimate the correlation to be here? So numerically, though, what value of R would you predict? Negative 0.7? I think it'll be a bit closer to -1 than that. But you're just guessing right now. You have no intuition about it. It's a fine guess. I would say, though, I'd be surprised if this wasn't better than 0.95. I'd be guessing it's probably going to be close to that good.
0.93.
Okay. So let's find the value then for R. Our calculator can do this for us. We don't have to do anything to do it. So I'm going to exit out of here back to the main screen. So second, and then the mode button will exit you to the main screen from any menu. I'm going to press the stat button once again. But this time I'm going to go over to the calc tab. And the command I'm going to select is linreg. That should be command 4. And again, here it's going to ask me what data am I going to use or create this linear regression for. I want it to L1 was my x's and L2 was my y's. That's what we graphed, right? So that's good. Frequency list we're never going to deal with in this class. Store regeq. Let's do that. So what this command is doing is it's going to create an equation for the best fit line for us. I want it to save that equation into the y equals menu, specifically into like the y1 spot. So I can go and I can graph that best fit line on the same axis as our data. Everybody okay with that? So what I'm going to do is retrieve the command y1 to go here. y1 is a variable, so I'm going to find that under the vars button. It's a y variable, so I'm going to go over to the y vars option. And we're graphing a function like a line, so I'll be under the function tab, and there's my y1. And then I'll just hit calculate. So here's my equation for my line. Did anybody get R values with it when they did this? No. Okay, well we can. Let's do that and turn on that option for us. Sound good? So the easiest way to do this is to go to the catalog. So I'm going to press the second button and then the catalog, which is the 0. Found it. And the command I'm looking for is called diagnostic on. So I could scroll all the way down to the D's, or I could just press the letter or the button with the letter D above it to skip all the way down to the D's. Or you could scroll. It's going to be a minute, though. And the command I'm looking for is diagnostic on. Have we found that command? Okay. Once I found it, I'm going to press enter. It's going to paste it onto the home screen. And press enter again. That'll say done. So what I want to do now is I want to do that same thing that I did before. So I could go through all those buttons to find the linreg. Or, since I'm doing the exact same command again, if I press second and then enter, and then second and enter again, it'll retrieve that linreg command for me. Then I can just press enter and it'll run it again. And I got that same slope-intercept equation, but this time I got the r value with it. Notice at the bottom. Yeah, you got r squared and then r. We'll talk about what r squared is a little bit later. Right now, we're just worried about r. Okay? So we saw that it's negative 0.96 and change. So pretty good, right? I had a pretty good guess when I thought it'd be a bit better than 0.95. It's like I've done this a time or two before. Let's also hit graph. If I hit graph, you'll see now that in addition to our scatter plot, the equation for our best fit line is now drawn in as well. It's pretty nice, right? Okay. So let's also show you guys how to do this with Excel. Well, I don't know if you'll do it in this class, but you'll probably do things in some kind of a class with it. You'll do stuff with Excel, and it's a nice skill to have. They probably have a big barn.
Yeah. I'd rather drive a Humvee.
Okay. So in Excel, I've gone and I typed in my data set. Stop talking, please. Okay. Everybody's good with that? Just typed in my data. I'm going to highlight my data set. And then what I'm going to go to is the Data tab. Nope. Insert tab, sorry. And I'm going to find my charts. And the option I want is a scatter plot like this. So there's my scatter plot. Excel has automatically chosen for me my X and Y axes, which is fine. It's a perfectly reasonable picture. What I'm going to do now is select the, where is it? The options command. And I'm going to click the trend line option. So there it's added in my best fit line. From the best fit line, I'll right click it, select format trend line. And I'll select display the equation on the chart and also give me the r squared value. And I can just move that wherever I want. And there we go.
That's good.
Did the same thing with Excel. We'll stop here for today.